computer. One question that came up with some, in a pre-class discussion and whatnot was for next class, right? So here we are talking about 7.3 in Monday's class. And Wednesday, we're supposed to be talking about 7.3/7.4. It would be really good if you came to class having watched the pre-class videos on 7.4. Because I do believe, assuming that we make a decent way through the notes for today, that we will begin talking about 7.4 on Wednesday's class. And so, yes, please watch the pre-class videos if you would before Wednesday. Otherwise, you'll just be a little bit lost maybe until you see those. Of course, we'll do a quick review and everything like we usually do, but it'll be better to have viewed those. Yes, a few of you have joined right on time. And yes, we talked about, I rearranged and basically just rotated my computer. I'm still downstairs and all that sort of stuff. But now you have like a glare from a window and stuff like that. So yes, things are a little bit different. If you have a question about partial credit and whatnot, there's an instructor who's in charge of partial credit, Valentina Madalena. You can reach out to her. Her email's on Piazza and on the syllabus. Let's see, where am I able to view the submission for the exam? You can go back to the exam, right, where you took it and whatnot. Of course, it's not going to let you take it again, but there's a little drop down. It's a small arrow just to the right of the header. And if you click that drop down, you have an option to view past submissions. So you view your submissions, and then you can go ahead and see what you got right, see what you got wrong, where was your partial credit submitted, all that sort, or where was your partial credit distributed, all that sort of stuff. And so, yes, it's definitely a good idea to review your exam, not only to study for the final, but also just to make sure that everything was graded correctly. Where are the cats? They're upstairs sleeping. All right, with that, let's talk about math. Well, in particular, we have been talking about math, but 7.3, right? 7.3 is about trigonometric substitution. We have a couple days to talk about this because it's fairly complicated. And so I think we do need these a couple days. There's this crazy set of rules right here, which is fine. If you like to memorize rules, by all means, you can memorize these rules. I'd like to emphasize in today's class about how, what we should be thinking about. Why are these the right things to substitute in? And really what it all comes down to is trying to cancel out a square root. That's kind of the initial idea behind this. Of course, you can apply this sort of stuff to things without square roots. But kind of in its heart, in its original kind of, why are we bringing this stuff up? Why is it useful? Is to try to get rid of a square root. And how do you get rid of a square root? Well, a perfect square does a great job, right? So if you can exchange somehow for a perfect square, then the square root and the perfect square will nicely cancel, and you'll be able to make some progress. And so we'll talk about this and try to emphasize that even more in today's class and the problems that we cover. You can see that these problems, again, a lot of them have square roots and whatnot. At some point, hopefully, you see right here, the square root cancels, right? And then you end up with one of these 7.2 problems, right? And so now we've reduced the problem into something that we solved last time. Remember in last class, we talked about how to integrate secant. It was one of the things right in a box in a pre-class video notes. We learned, well, of course, we've seen before the integral of tangent was the natural log of the absolute value of secant of theta. And then we got also that the integral of secant is this thing here. I would have this memorized if you would, especially for like a quiz. It's given on the formula sheet for the exam. But this is one that seems to come up a decent amount. And so it's good to just have it, at your fingertips. All right. And yeah, I mean, we just see several examples in a row of how do we apply these rules that we had before. Sometimes this one wasn't so bad, but you saw one certainly where we had to make like little triangles and we had to kind of trade in, and we practiced this a little bit in chapter 6, right? But for instance, here we had integrated and we had gotten cotangent of theta, and we needed to know how to simplify this, right? We knew already that sine of theta was equal to x over 2. Again, we're trying to get back to x's because that's what the problem originally gave us, x's. And so it's like the same thing with u substitution. Anytime you have u substitution, the last step is always to swap back, and instead of u's, you write everything's in terms of x. So here we want to know what cotangent of theta is in terms of x's. We know what sine of theta is in terms of x's. And of course, the answer to, find this exchange rate is to make a triangle, right? And so we did this a fair amount in chapter 6, and now you can see how it's being used as part of these trigonometric substitution problems here in 7.3. And so, yeah, that's the bulk of it. That is 7.3 in a nutshell. Again, it is fairly complicated. There's lots of steps. It certainly deserves, we have a day and a half for it. It probably deserves that. It probably deserves more. But that's what we're going to be talking about today. I thought I had seen some hands go up and down and stuff like this. Any questions before we jump into the new problems for today? Will, you got the floor.
Yeah, I heard someone mention that the first question on WebWork 7.3 was unsolvable. And I just got stuck. I got stuck at the end there evaluating the final integral, and I just wanted to see what you had to say about that.
I don't think this problem changed from last semester to this semester. And so as far as I know, it is indeed solvable. I haven't gone through this one myself recently. And so I don't know it off the top of my head just to be able to tell you, oh, this is what you do, or ramble off the correct answer. We'd basically have to start from scratch and solve it. So, I mean, I would be happy, I have office hours tomorrow and whatnot. If anyone wants to come and hang out, during office hours, I'm sure, someone will ask about this and we'll go over it.
Okay. All right. Thank you.
Yeah, of course. All right. Let's just double check here. Anything going on in the Q&A, Yuan?
One is asking, typically, do the exam scores get better or worse as the semester moves on?
Okay, so when you say typically, it's a little bit hard because, right, we only have one semester previous to this that's anything really like our semester, right? A lot of things changed when we went online. One of them being, right, instead of 2 exams at 90 minutes long each, we now have 3 exams, right, at 60 minutes long each. And so I would say, from last semester, I believe that exam 1 average was fairly good, like ours, I would say. Exam 2 and exam 3, traditionally, right, the content's a little bit more difficult. And so we usually see a drop. But I don't know how they relate to each other necessarily. Some students like chapter 7 more, some students like chapter 11 more. It's hard to necessarily say, everyone finds one easier or harder. Good. Any other questions, Yuan?
How the inverse relates to a function when substitute into the antiderivative? Are we substituting the inverse of something or just using its domain?
Yeah, so some of the problems you have no choice, right? The answer is an inverse trig function. And so in particular, like if you have theta in your ending answer here, you probably don't have a choice that it's going to end up with an inverse trig function. And so the domain is restricted. It's not restricted by the process of doing the integral. It's actually always restricted, right? You can see this right here. You're not allowed to plug in negatives into your square root. So actually, this is already restricted here between -3 and 3. In fact, these should probably be parentheses here, because if you plug in either -3 or +3, you end up with taking the square root of 0 and then dividing by 0. So, right, the square root of 0 is no issue, but dividing by 0 is an issue. So actually, this function itself, you could ask, what is the domain? And then look at the ending answer and ask for, right, what is the domain of this thing? And it turns out, right, they're the same. And so the inverse function doesn't restrict the domain, for problems like this. But I mean, they coincide, and sometimes they also have, restricted domains. Whenever possible, and you will encounter this in web work, for things like this. And this is a good point here. So we wanted cotangent of theta, and we drew this triangle and we got everything to cancel. Whenever you have a composition of an inverse trig function and then a trig function, you should simplify this. So that is to say, right, even though we have theta is equal to sine inverse of all this stuff, right? We did not write our final answer as cotangent. Oops, first of all, that's a horrible T. Cotangent of, and then theta, and just plug this in, sine inverse of x over 2. So we did not just write it like this, because again, we have a composition of an inverse trig function and a trig function, and this should be simplified down. Web work will help kind of get you guys used to doing this and kind of forcing you to, whenever it doesn't want an inverse trig function, it'll let you know. And likewise, when it comes to quizzes and exams and stuff like this, right, you would never see, for instance, on a multiple choice, this as a final answer. Just don't write it like that, right? You would write it like this. And so you need to be able to switch this, right, using this triangle here into, this function up here, because that's what we would show on a multiple choice question, right, is that final answer. And so this is training you guys for what, is expected of you for quizzes and exams, the final, all that sort of stuff. So I understand sometimes it's frustrating that web work doesn't allow you to do this, but it's for a good cause, Good. We maybe have, well, it's already after 2. We got to go. Let's do some new problems here, and then I'll make sure to call on some folks, as we're doing problems. So the first problem that I'd like to do here, this one specifically says use trigonometric substitution in order to evaluate out this integral. It says this because, of course, when you look at this, right, you may identify that this looks awfully sine inverse E, right? If this had been the integral of 1 over the square root of 1 minus x squared dx, this would be just regular old sine inverse. However, of course, we've dealt with situations where you have this 4 here before. And so one way to do this is a chapter 6 style method, or here it says use trigonometric substitution. And so I just kind of wanted to highlight some of the key things with trigonometric substitution for this problem here. And of course, we can double check that we get the same answer, because at the end, hopefully it looks like sine inverse of something. Okay, so the very first thing, and kind of I talked a little bit during the pre-class notes, right? A lot of what we're doing with this trigonometric substitution is trying to create a perfect square, right? I've already said to you guys that square roots are a bit of a monster here when it comes to antiderivatives. And so somehow we want to get rid of this, the square root. And so what we're going to do is make some substitution using our trig rules. And in particular, all of this again starts with this business of sine squared theta plus cosine squared theta is equal to 1. And so let me go ahead and rearrange a little bit. And what I'm going to do is just subtract away the sine squared on both sides. And we get cosine squared is equal to 1 minus sine squared. This is important because, first of all, we have a constant. Ours is a little bit different. Ours is a 1, while we want a 4, minus a variable squared. So we're trying to get this general form. And you can see that if we could successfully make what we have, close to this 4 minus x squared here, then we could trade it in for a perfect square, right? Cosine squared is a perfect square. So therefore the square root and it would cancel out and life would be grand. So the question that we need to pose ourselves right now is, well, how do I deal with that 4 there? And of course, what we're going to do is multiply through by 4 on both sides. So we're going to have 4 cosine squared theta is equal to 4 minus 4 sine squared theta. So I just multiply by 4 across the board. Now we can see, right, what we have versus, what we want, 4 minus x squared. We can just set these equal to one another, right? So I'm going to go ahead and set x squared. This is what I would like to evaluate out. And this is what I have, 4 minus sine squared theta. And so now if you take the square root on both sides, you see that the correct substitution should be 2 sine of theta. Now, this is a little bit of a roundabout way of, coming up with what the correct trig substitution is. Of course, if you'd like to, you can just memorize this table. But this table, you'll see, does not cover every possible situation. And so knowing kind of why you're making these substitutions, I think has a lot of value. So again, we were in this first case right here. We had the square root of some constant squared. In this case, I was 4 or 2 squared is going to be this right here. Oops. So again, this table is fine, but we'll run up against some situations that are not covered by the table. And so it helps to understand kind of why you're doing these things. Again, we're trying to make a perfect square. With this substitution right here, we're going to end up being able to substitute into our square root 4 cosine squared. So let's go ahead and do that really quick. We have 1 divided by, and if I use this substitution, again, we've already seen if we square both sides, and then if we kind of rearrange a little bit, right, we get that the 4 minus 4 sine squared theta is the same thing as 4 cosine squared theta. One extremely common mistake, and it's like the #1 mistake for all of these problems, is that folks forget, either just outright forget to write dx or d theta, or they just exchange and they start writing d theta. They say, okay, well, I want to integrate with respect to theta, so I'm going to write d theta here. But remember, right, ours is dx. And just like when you're using U substitution, you have to figure out the exchange rate, right? It's quite often not the case that dx is just equal to d theta. Usually there's some, again, exchange that you need to use based on these derivatives. So if we take the derivative of both sides of this, we get that dx is equal to 2 cosine of theta d theta. So again, I don't put it somewhere in your notes, star it and everything, that really you do not want to forget to exchange your dx for some amount of d thetas. They are probably not, equal to one another. And so you do need some exchange rate here. And again, if you don't write this, and this is kind of the #1 thing that I see, is that people just don't write it. And they assume that we're integrating with respect to theta already, you lose it, right? And so again, instead of dx, really what I should have here is 2 cosine of theta d theta. That's what my dx is equal to. All right, I've been going for a little while. I've seen hands go up and down. I've seen notifications come up with the Q&A and everything. I'm sure there are questions about this. So let's take a few questions before we push on and see the final result. Arian, I think you have the first question here.
Hi, this is more of a logistical issue. So basically for Wednesday, you've written it 7.3 and 7.4, and I was wondering
Yes.
what that's about.
We have more time. 7.3 and 7.4 are complicated long sections. And so we'll cover as much as we can of 7.3 in today's class. And then in Wednesday's class, we'll finish up 7.3, give more time to it, and we'll begin 7.4. Now, we're not going to get all the way through 7.4. So that way, that's why Friday's class is also 7.4.
All right, but is there going to be any new information that we'll need to complete the web work, or can we just like finish everything today?
For 7.3?
Yeah.
It's possible you could, do it all with today's material. I mean, it's possible you could do it all with just the pre-class notes.
No, I tried that. It was awful. I need this class.
Okay.
Ryan, you don't understand how special you are.
Oh, I see. But yeah, so anytime, right, if you can't get through it, and I think we have the due date for the web work is based off of Wednesday's class, because that's the last day that we cover the material. So I believe the 7.3 web work, and feel free, I'm sure everyone will correct me if I'm wrong, I believe it's due on Friday. But yeah, certainly working ahead is good.
All right, thank you.
Yeah, no problem. Hey, I got it right. Good. I know that's what we intended it to be. Yuan, do you see anything going on in the Q&A? Maybe we could do one of those, and then I'll call on one more person for the who has their hand raised.
Why is 2 cosine instead of 2 sine?
Well, we set our x value equal to 2 sine. So in that case, we did use it. But right, based on that, we had to take the derivative to figure out the exchange rate for the differentials. Right, so dx was equal to 2 cosine of theta d theta. So we do actually see the appearance of both. It's just one you set for x and one you find for dx.
I actually have a question is, you can set 2 sine or 2 cosine, right? That doesn't matter.
That is a fun question, and it's one that usually comes up. So you saw in the pre-class video notes, and you see here that we rearrange for solving for cosine squared, right? With 1 minus sine squared theta. So that's kind of the natural exchange rate that we bring up. And Yuan is correct in the case that you could instead, I don't know what, I'll use orange here for careful. You could instead rearrange this and make sine squared theta equal to 1 minus cosine squared theta. And you have some substitution like x is equal to 2 cosine of theta. Why I put this in orange and be a little bit wary about, because notice that when we did our exchange, we got some cosines, and in particular, our cosines were in the denominator. Now, it's very possible, unlike in this situation, that they won't cancel out. And you could end up with something like having to integrate 1 over cosine squared theta. We'll say after everything, this is some alternate problem. So this right here is the integral of secant squared. Now, many of you know from your calculus 1 days, the integral of secant squared like that, right? What's the integral of secant squared? Someone's got it, I'm sure. Yeah, I see it. Tangent. Now, on the other hand, if you were to do this other way, which again, I wrote in orange here, maybe you would get sines instead of cosines. So you have 1 over sine squared theta d theta. That's the same thing as the integral of cosecant squared theta d theta. What I find is that we're just not as fast, right? We don't have this one necessarily put to memory like we do secant squared theta. And maybe, you know, if you took calculus 1 someplace else, and you know you're very familiar with this, then yes, maybe you do have this one memorized. It's not quite cotangent, but it's negative cotangent. That's absolutely correct. And so that's why I put this one in orange. It's not that it's wrong. It's just that if you go this method, first of all, you stand a minor chance of confusing graders, which is never a good thing. But also you have to be much more well-versed in 1 over sine stuff rather than 1 over cosine. And so likewise, we learned in class, right, we know the integral of secant of theta, d theta. And I told you all to have this memorized, the natural log of the absolute value of secant of theta plus tangent of theta plus a constant of integration. So if I asked you what is the integral of cosecant of theta, right, this is something that could come up if you decide to go this other method. And so yes, it's possible, but you have to memorize a different set of rules. You have to be comfortable with a different set of rules. And so that's why I would recommend not going that way. I would try to get more cosines in my life. We seem to be more comfortable with cosines and integrating cosines and even 1 over cosine like secant. So that's why you just have to be a little bit careful.
I got another general question. I'm sorry.
Okay.
Is that can you take because there's the table includes the arc sine inverse, which is 1 over 1 square root of 1 minus x squared. Can they use up directly dividing the up and down by 2, and then use up directly and use the arc sine?
Not for this problem. It says use trigonometric substitution. You wouldn't be using trigonometric substitution.
Okay,
So
okay.
I was careful with my wording. Yeah.
Okay. If it's required, then you have to use that. Okay.
Yeah. If it was an
it's
open,
not-
if this is a fine or maybe even excellent final exam problem, because students could, especially if it didn't say, if it just says evaluate. Some students can use the chapter 6 method. Some students can use the chapter 7 method, and you both get the correct answer at the end of the day. So, and of course, the final exam is interested in testing over both chapter 6 and chapter 7. So maybe this is a fine place to put something like that. Noah, you got the last question here, and then we're going to finish this problem.
All right. Can you hear me?
Yeah, sure can.
All right. I was just a little confused as to why exactly we're using theta in here instead of x. I know you kind of touched on it a little bit earlier, but I'm still just a little confused by it as why theta is within the trig functions instead of sine, or instead of x. I'm sorry.
Again, we're trying to do some sort. It's like a U substitution, and so you need to choose a different variable name. Otherwise, right? If I just wrote that x, we're going to substitute in for sine of x. I haven't created a new variable that's based on another one, right? I've made some equation and you could probably solve this. For instance, x equals 0 is one solution to such equation. right? And so we need to use some different variable name. Otherwise, you're actually creating an equation and you could, solve this equation. So it's like the U substitution where we do like U is equal to X squared rather than X is equal to X squared. So at the surface level answer to your question is we need to use a different variable name. So that way we don't confuse ourselves, confuse the grader, and accidentally make some connections that aren't really there. Does that kind of
Okay.
make sense?
Yeah, that definitely makes sense. Thank you very much.
Yeah, of course. All right, let's finish up this problem. And then I'm sure there are a few more questions that we need to take here. Again, our reason why we were doing this was to get a perfect square inside of our square root. Now that we have that perfect square inside of our square root, like things nicely cancel out. And so we get 2 cosine of theta. And again, in the numerator here, we have 2 cosine of theta, and these excellently cancel out, right? Completely cancel here. And then we just have the integral of 1 with respect to theta. So when you do the integral of 1, you get theta. Oops, I shouldn't have the integral. I just did that. So the integral of 1 is theta plus some constant of integration. And now we need to, again, the problem was originally given to us in terms of x's. So we need to exchange back for x's. So we go back to our original equation that kind of told us the connection between x and theta. And we need to rearrange this, right? So we're going to go ahead and divide by 2. Then, well, we need to cancel out the sign. And so, of course, to cancel out a function, you apply its inverse. So we apply a sine inverse. And of course, on that right-hand side, they do perfectly cancel out. And so we get the sine inverse of x over 2 on the left-hand side, and that's what's equal to theta. So our final answer is sine inverse of x over 2 plus, of course, our constant of integration. Now, we talked about in the pre-class video, and it turns out it'll always be the case in the problems that you get here in this class, that there is some technicalities that I'm sweeping under the rug right here. Technically, when you take the absolute value of something squared, you don't exactly get back to where you started. It's always positive, right? And that's why typically when you take an absolute value, right, you have to have the plus and the minus, right, is to account for both of these sorts of things. However, with the domain restriction that we have, and again, we go into this, a fair amount of detail in the pre-class videos, it turns out that cosine will always be positive on this restricted domain. So in particular, for our sine inverse stuff here, or for this, we take an interval from negative pi over 2 to pi over 2. And on that interval, right, it's quadrants 1 and 4, cosine is always positive. And so that's why you don't really need to worry about the absolute values. So this will be the last time here that I'm going to even talk or mention about these absolute values, because again, it always works out with the domain restrictions that we choose when we make this substitution, that those absolute values just go away. Okay, so I think I've explained this as well as I would, would like. Ish. I'm sure there are questions though, because again, this is tough stuff. So maybe let's first go to Q&A. Yuan, are there any questions out there?
So someone is having trouble with integral. So just how do you know when you're done using the integral sign and not get to solving?
When you actually do the antiderivative, that's going to be the right time to lose the integral sign. So there was a fair amount right where I just, maybe in this step right here, I plugged stuff in. And then in this step right here, I simplified, right? I didn't actually do an antiderivative. I simplified down to just 1. And then I actually took the antiderivative of 1, right? And so the antiderivative of 1 became theta. So once you actually use the antiderivative, that's when you lose the sign. You've used it up. Right? If I had tried to take the antiderivative back here, I would have lost it, right? But we didn't. And so it kept around because we just did some simplification. We never actually did an antiderivative until the final bit here. Good. Let's call on a person with a raised hand here. Jeff, you got the floor.
Thank you, Professor. I was behind writing down the notes, so I didn't hear what you were explaining when you superimpose the 4 cosine squared for x squared and what happened to that constant of 4 and the negative for the 4 sign?
Sure. So yeah, again, our strategy was to replace what we have. And again, in our case, it was this 4 minus x squared. We were trying to replace that with a perfect square. If we could somehow get a perfect square under the square root, life would be grand, right? Because then they can cancel and we can actually stand a chance of evaluating this. So we're trying to replace it with a perfect square. And it turns out when you have things like this, a constant minus a variable squared, that this aligns very closely with our good old Pythagorean theorem. Now, this looks very similar to our 4 minus a variable squared, but we have a 1 in this line, not a 4. So of course, the way you fix that is by multiplying through by 4 across the board. And now you have things perfectly lining up. You have 4 minus some variable squared.
Right.
So, well, you take with, what you have with what you want, and you set them equal to each other. What we have is x squared. What we would like is that to be 4 sine squared theta. If we could get it to be 4 sine squared theta, again, we could substitute all that stuff in for a nice, beautiful, perfect square. So again, we set up that equation, what we have with what we want. X squared is equal to 4 sine squared theta. And we can solve for the correct substitution to make. In this case, x equals 2 sine theta. Now, I went through this bit a little bit fast just because it's something that we did in the video. But, and again, we chose all this for a very specific reason. And that's another, I guess, reason why I didn't mind going fast through this. But maybe it's worth it, for one more time here to go through all of the steps, right? 4 minus and x squared. Again, x is going to be 2 sine theta. When you go ahead and you simplify that squaring function, right? You get the square root of 4 minus 4 sine squared theta. That's all under our square root. And again, 4 minus 4 sine squared theta, that's exactly this line right here. That's equal to the integral of 1 over the square root of 4 cosine squared theta. We were able to exchange for a perfect square. And again, that's the whole setup. We were trying to exchange for a perfect square, and we succeeded finally.
So you're not saying the x squared is 4 cosine squared theta?
No, it's all of it.
Because I was following the flow down and thought that was continuous, that somehow x squared became 4 cosine theta, which equaled 4 sine, which didn't follow. I was like, okay, thank you.
Yes. Yeah, that's a very important point, that it's really all of it. All of it we get to exchange for, right? The 4 and the minus x squared all come with it to make the perfect square for cosine squared theta. So yes, very good point there. Okay, with that, why don't we, do you have any big questions in Q&A or chat, Yuan?
No.
Excellent.
Mm-hmm.
Well, let's press forward then. As promised, this is a situation that doesn't match up with what we have in our table. In our table, you might have something like when you have a plus x squared. Oh, sorry, a squared plus x squared may be one of the things in the table. And so if you just have the table memorized, you'll look at this and you say, I don't know what to do, right? But if, again, you have the strategy memorized that we're talking about right now and trying to exchange this for a perfect square, you'll be able to solve this problem. And so again, I think it's more important to understand kind of what you're doing, exchanging for a perfect square, rather than just memorizing a lot of things in a table. And so again, just like last time, we're going to start off with cosine squared theta plus sine squared theta is equal to 1. And you saw that there was a couple of times, right, that switching to the tangent and secant view turns out to be important. Which, by the way, if you try to, rearrange this and solve for 1 plus, you'll see that it doesn't really work out so great with the 1 plus, right? Because you can do 1 minus very well, but you can't really do 1 plus. And so by dividing through by cosine squared across the board, we get 1 plus tangent squared theta is equal to secant squared theta. So again, I divide by cosine through, and this is kind of the other classic Pythagorean theorem formula. And now you can see that if we were to get 4x squared to be equal to tangent squared theta, well, then we'd have a perfect square, right? We could exchange all of it, the 1 and the tangent squared theta, and we would get secant squared theta. And so our goal becomes setting, what we have, 4x squared, equal to what we want, tangent squared. And with this, well, we can rearrange a little bit. X squared is equal to, 1/4 tangent squared. Take the square root, we get 1/2 tangent theta. My end's not very clear here. 1/2 tangent theta. So if we choose this for a trigonometric substitution, the claim is we'll get a nice perfect square under our square root, just like we'd like. And then that'll cancel out and we'll actually be able to evaluate this. And so let's just double check here. Let's do the integral of 2 over the square root of 1 plus 4 x squared. So x squared is the same thing as 1/4 tangent squared theta. So that's what I'm substituting in for x squared. Now let's go ahead and simplify a little bit. We see the 1/4 and the 4 are going to cancel out very nicely. And we're going to get 1 plus tangent squared theta. And now 1 plus tangent squared theta. Well, remember, we're getting what we wanted, right? 1 plus tangent squared theta, that's going to be secant squared. So this is going to be secant squared theta. Of course, in the square root, we already talked about how these things will nicely cancel. And now this is what we're going to need to evaluate. And then you yell at me, what am I forgetting? Yeah, a lot of you guys caught it. Excellent. I fell into this trap, right? Again, because we want to emphasize here in class, right? Don't just stop writing the dx versus d theta. You always have to exchange. Right now, this is dx. And so if I was to just continue past this, right, starting to evaluate out my antiderivative, I'm going to get the wrong answer. And so we need to, at some point, exchange, right, our dx for our d thetas. It's not enough to just exchange x's for thetas. We also need to do, this final exchange here. And so let's go ahead and calculate out what the exchange rate is. dx is equal to 1/2 secant squared theta d theta. And so instead of dx, we're going to write 1/2 secant squared theta d theta. And now we've taken this successfully into account. We can see that the 1/2 and the 2 will nicely cancel here. Let's see, secant squared theta d theta. And at this point right here, you can see that there's going to be some cancellation. So a secant on top, one of the secants on bottom. I guess since I canceled the 2 and the 1/2, I should go back and rewrite these correctly. And so now this just becomes the integral of secant. And like I told you at the top of the class, right, I would have this one memorized. And so the integral of secant is going to be the natural log of the absolute value of secant of theta plus tangent of theta plus a constant of integration. And now we get to our final step. We have solved this in terms of theta, but of course the original problem was given to us in terms of x's. And so we would like to exchange back, right? Instead of x's, instead of thetas, we need to write it in terms of x. So let's go back to our original equation here. So, and we're gonna try to solve this for a few things. I'm gonna write this as 2x is equal to tangent of theta. So you can see that we actually have one of them right away, right? So I just multiplied through by 2, and we were able to solve for tangent of theta. So that means that this bit right here is just gonna be a nice, beautiful 2x. On the other hand, for secant of theta, this is going to be one of these cases where we need to use these triangles, right? So we know what tangent of theta is. We need to get secant of theta. So let's go ahead, build one of these right triangles. Here's our angle theta. Remember, tangent is supposed to be opposite over adjacent. So, well, I see 2x. Let's make it 2x over 1, just so that we have a fraction. and we can make an opposite over adjacent. So we'll do opposite over adjacent, 2x and 1. Now remember, my goal is to find secant of theta. Secant is just 1 over cosine. And cosine, we remember from SOHCAHTOA, right? This is supposed to be adjacent over hypotenuse. So instead of dividing by a fraction, you're allowed to multiply by a reciprocal. We're going to be searching for hypotenuse over adjacent. That's going to be our final result. Well, we need hypotenuse over adjacent. I know what the adjacent is. That's just 1. But I don't know what the hypotenuse is. So this is where we have to use the Pythagorean theorem. So if we use the Pythagorean theorem, square each of these pieces, take the square root, that's going to be the hypotenuse squared. And then of course, we apply that square root. And so that's just the hypotenuse's length there. And so secant of theta is going to be hypotenuse over adjacent. So this is going to be the square root of 1 plus, let's simplify this down a little bit. That's going to be 4x squared once we distribute that squaring, and divided by adjacent. Hypotenuse divided by adjacent, well, adjacent's just 1. So we could kind of forget about that, simplify that down. And this right here is our absolute final answer. This is what we're looking for in web work. This is what we're looking for, if this is a D2L quiz or an exam or whatnot, if this is multiple choice, this is exactly what would be listed as one of the answers. And you choose that one. Okay, so yeah, I'm sure there are questions about this. I didn't pause in the middle of this one, so let's go ahead and take a few here. Ian, I think you are next on the list.
Oh, I'm sorry. This was actually from earlier, but you answered it a while ago.
Oh, okay. Well, wonderful. Then moving down the list here, Aditya, you got the floor.
Hi, can you hear me?
Yeah, sure can.
All right, so I was actually solving this problem in my head when you were doing the previous problem.
Okay.
So I'm actually one of those people that like to use the table that was given intro videos.
Sure.
So is it possible that you can factor out like factor the denominator, the square root, to where it becomes 1 or like a constant plus x squared?
Yes, and that's a good point. That if you would like to have the table memorized and use that in this case, that certainly does work. And so what you need to do is you need to factor out a 4. And so of course, this is going to become an x squared. And then your other term is going to become 1/4. And so now we can go ahead and remember with the square roots with multiplication, you're allowed to apply it to each piece. So the square root of 4 is just 2. And then the square root of this is, well, just what it is here. And so now you can see that the 2's would cancel on top and bottom. And remember, this is your a squared. And so therefore a would be equal to 1/2. And so it's maybe not surprising, right? When we went and we saw the correct thing to substitute in, right? The a was 1/2. And so yes, this certainly will work. So yeah,
work all scenarios.
Yeah, there's a way to do it. You have to be a little bit clever, right? And rearrange it into a way that actually fits the table. But yeah, if you do that, you can use the table on this one. Absolutely.
All right, thank you.
Yeah, of course. Yuan, what's going on in the Q&A?
First question is, how do you know it's using 1 plus tangent square equals sec square instead of cosine square plus sine square equals 1?
We're trying to match up one of these Pythagorean identities with what we have. And what we have is a constant plus a variable squared. Constant plus a variable squared. And so if you look at this right here, right, our only constant is 1, and we have variable squareds. But if you rearrange this, and if you pull either one over, right, you're going to get 1 minus a variable squared. So 1 minus sine squared theta is equal to cosine squared theta. That's kind of the classic one there. And so sadly, you don't have a plus there. And so sadly, yeah, this one doesn't happen to work out, giving us a nice perfect square on the other side. So yeah, tangent and secant will end up being better here. And it turns out, when we divided through by cosine squared on both sides, it did end up being this nice form where we have 1 plus a variable squared. It does take maybe, let's see, is this the one where there's another way to rearrange? No, not really. Yeah, so yeah, this is the only thing that works. So.
Mm-hmm. And the server is still asking where is the 2x equals tangent theta comes from.
Yeah, so that comes from remember at the very end when we go back and we exchange our thetas for our x's, this always comes from our original exchange equation. So we did a lot of work to figure out what is the correct substitution. How many thetas should be worth an x? In this case, it was 1/2 tangent theta should be worth an x. And so you use that to rearrange, to swap back in terms of x's from our thetas. So I multiplied by 2 on both sides, right? And when I did that, I got this tangent of theta is equal to 2x, which it turned out one of those things, right? One of the things we were searching for was tangent of theta. And so we were able to substitute that in immediately. And then we had to do more work to get secant of theta.
And the one more is asking, can they do a substitution u equals 2x and solve for u equals?
That would be equivalent to this right here. So yes, if you do first a u substitution and then you want to use the table, that will also work. All right, we only have a couple minutes left. Let's try to get through one more problem here. And here it is. So square root x squared minus 9 over x dx. And so I'm going to go a little bit fast through this one since we only have 3 minutes. We'll stick around after to answer questions about this. So again, we're going to be starting with sine squared theta plus cosine squared theta is equal to 1. We would like to get a variable squared minus a constant to be equal to a perfect square. And this is the one that I was trying to think about for the last problem here. This is the one where you can kind of get tempted and do a sine squared theta minus 1 is equal to negative cosine squared theta. So here you have a variable squared minus a constant is equal to a perfect square. If we multiply through by 9, then it starts to line up kind of as good as you could hope. Oops, minus, there we go. The only issue is imagine that we do this substitution, right? And we get this exactly equal to this, right? We set up our x's beautifully and we exchange and all that sort of stuff. And so we get to finally put this in our square root, a nice perfect square inside of our square root. Who can see what's wrong with this? Who can see we have a negative inside of our square root, right? So that's going to be an issue. We're going to start having imaginary numbers and then we start doing complex analysis and then we get very sad, right? There is complex calculus, but luckily we don't have to do it, right? And so this sadly, right, does not work out. And so this is a good time, a good indicator that we should exchange for our tangents and our secants. And we'll see that this does work out. So if we divide through by cosine squared, we get our tangent squared theta plus 1 is equal to secant squared theta. And now when you rearrange this, you get secant squared theta minus a constant, in this case 1, is equal to a perfect square, but it's better than that. It's a positive perfect square so that we can actually put this thing into a square root and survive. So now we're going to multiply through by 9. 9 tangent squared theta is equal to 9 secant squared theta minus 9. And again, we take what we have, in this case, an x squared minus 9, and we're trying to make it line up with what we want. And that is, if we can make it look like this, then we can exchange this for a nice perfect square. And so we're going to set x squared equal to 9 secant of theta, 9 secant squared theta. So therefore, x is going to be 3 secant of theta. And for those who like the table method, you already saw this, right? If you memorize the table and you just know it, then yes, you know right away that a is 3 and we should be using a secant substitution. Let's go ahead, once you start doing a lot of these, you realize you just need to calculate dx. We might as well do it now. So 3 secant of theta, tangent of theta, d theta. We're going to end with the correct transformation into thetas. And then that'll be where we end for today. So this is going to be the square root, sorry, the integral of the square root. And again, if we made this perfectly line up, so that way inside of our square root, we're going to end up with 9 tangent squared theta, right? With this substitution of x equals 3 secant of theta, x squared becomes 9 secant squared theta. And then remember inside here, we have that minus 9. And so we get our 9 secant squared theta minus 9. And we can substitute in for that 9 tangent squared theta. Now in the denominator, we still have an x. So that's 3 secant theta. And instead of dx, we're going to write 3 secant theta tangent of theta d theta. We can see that there's some cancellation that happens. The square root of 9 tangent squared theta is going to be 3 tangent theta. And we have another tangent theta. So this is going to be tangent squared. Yeah, this is where we're going to end. So the question becomes a 7-2 question, right? How do you integrate tangent squared? And so, okay, this is where we'll begin next time. We'll talk about how do we integrate this. And you can see that we have a few problems left. So for those who were asking at the beginning, right, what are we going to be doing in Wednesday's class? Well, I'll finish up this one. We have 2 more problems here to ponder. This one's maybe the most difficult one. And then we're going to start talking about 7.4. So that's going to be Wednesday's class. We're going to finish up these last 2 problems and then start talking about 7.4. All right, so that's a good place where we'll formally end. I'll go ahead and stop the recording.